Right. Hello guys. Welcome back. This video, we're gonna introduce 14.4, the tangent planes and its linear approximations. So previously we have already defined the domain and continuity for a multi-variable function. And in 14.3, we already introduced the partial differentiations, which characterize how a function moves along the x direction and y direction. And today we're going to characterize the differentiability. So in this section, we want to extend the concept of differentiability to 2D space, 3D space, higher dimensional space. And a natural question might arise. So if you guys remember, in the 1D case, we often just characterize differentiability as being differentiable, right? Namely that you can differentiate a function, that is differentiability. So in this 2D and 3D case, supposedly if we can partially differentiate a function with respect to x, y, and z and w, say you're in four variable, then why does that not characterize as differentiability? So let us rephrase this. Actually, differentiability is not only the existence of the derivative, it actually means that we want to approximate a function by a linear function. So let us sort of rephrase how we define differentiability in the one-dimensional case so that we can see how we can extend that definition towards the one-dimensional case. So a differentiability for a single variable function can be at a particular point x equals to a can be rephrased as following. So we simply say that the existence of a tangent line means that the function is differentiable. I know that this definition is sort of equivalent to the existence of derivative, right? Because having a derivative, then you would immediately have a tangent line. The slope is given by the differentiation, right? So you see that given a function, this blue function, then it is differentiable in the sense that at a point A, in the sense that the tangent line actually exists. And why is tangent line so important? So you can see that tangent line actually looks very much like the function near the point, right? In the sense that if you go and zoom in the function, then at a point, then those two almost coincide. So this is called a let's say it's a first order approximation, where zero order means something that simply has the same value as f of x at the point A. So for instance, these are all zero order approximation, which does not make much sense because it only approximates the point itself only. It coincides with the value, but not near the value. So the first order approximation or a tangent line, those are interchangeable phrase, simply means that not only do the line intersect the curve, the graph, at the corresponding point, and also near the point, it looks very much like the function. So that's what we call a first order approximation. Not only the point is the same, only also the points near the x equals to a is also closely related to the tangent line. So you can see that you can never find a tangent line for this blue curve because however you draw the lines that pass to the corresponding point, a f of a, none of this line will be a good approximation for the value of the function near the point A when x is close to A. Simply because that when we zoom in, you see that there's always a difference between the actual function and the so-called tangent line. So there will be no tangent line. In this case, it is non-differentiable, even if it is continuous, right? So I hope that sort of help you guys realize that differentiability simply in the one-dimensional case means that you can approximate a function at a particular point with a linear function. That is differentiability. So in this case, let me first consider a two-variable case, f of x, y. Instead of a tangent line, now we have to find a tangent plane because you're working with a two-dimensional surface. So to find a linear function that approximates that surface, you have to be a plane, right, instead of a line. you have actually multiple different lines that can approximate the surface, and those multiple lines gives the components of being a plane. So first of all, let us first motivate ourselves with the equation of this so-called tangent plane instead of tangent line. Previously, in the definition of the partial differentiation, we know that the derivative, the partial derivative fxab is basically the rate of change of this function near along the x direction, right? So you can see that I set the 0 here because y is not moving actually. Y is always the same on the same plane, whereas the slope of the z within the x goes along by 1 towards fxab. That is the definition of slope, right? So basically that vector, which is a tangent vector towards the surface at the point AB, will be parallel to this vector, 1, 0, fxab. Similarly, for the directional differentiation along the y direction, the partial derivative in y, it represents the rate of change of moving y by 1 unit and z by fyab units, right? So basically, we get two tangent vectors, u and v. And why are those useful? So those are two tangent vectors at the point AB of the surface, right? And they must be orthogonal to the normal vector of the plane. So it goes back to how do we find the equation for the plane? We need the normal vector, and we also need a point, right? The point is kind of free because we already have AB f of AB. That is what we want. And for a normal vector, as I mentioned, those two guys are orthogonal. So we can apply the cross product to see that by taking the cross product of u and v, we have 1, 0 fx, 0, 1 fy, which eventually we get minus fx, minus fy, and 1. So this will be parallel to the normal vector here. So just for convenience, let me choose the negative sign of this guy. So fx, fy, and so there should be 1 here. My bad. 1 minus 1. Okay, so this is simply the opposite direction of the normal vector here. Right, so according to what we have learned in 12.5, that the equation for plane E can be given by a normal vector, taking dot product with the difference between the point xyz and the point on the plane AB f of AB. If you write it down in terms of, again, I missed a negative sign here. If you write it down in terms of scalars, you will get fxab times x minus a, which is these two taking dot product, and fyab multiplied by y minus b, and then finally minus 1 times z minus f of ab. So then we can rearrange it into z equals to f of ab plus these two guys. It looks very familiar, right? That's because in the one-dimensional case, the tangent line is actually given by y equals f of a plus f prime of a x minus a. So you can see that this basically serves as the so-called zero-order approximation. They share the same value at a point A. And this accounts for the first-order approximation. So it looks, the linear function looks nearly like the function near the point A. And here it's the same, exactly the same logic. So this function obviously shares the same value as the function f at the point AB. And also, it approximates the point AB near the point AB, right? So let me emphasize on this. These three guys are just numbers, right? So this is a plane. The only variable here is x, y, and z. It's a linear function. There is no quadratic term or strange transcendental function like sine, cosine, exponential. Okay? So from now on, let us call this kind of equation a tangent plane. But technically, we haven't defined it yet because we still haven't defined differentiability in a precise way, which we will do later. But for now, we first try to evaluate an example so you guys have a understanding of how this works. So let's evaluate the tangent plane of this function, z equals to ln of x minus 2y at the point 3, 1, 0, right? Okay, so if we set this function f of xy to be ln of x minus 2y, then by our technique in a previous video, we know that by taking the partial differentiation against x, gives us 1 over x minus 2y, where if you plug in the corresponding point, you have 1. And the same thing happens for fy by x minus 2. So by our formula here, the so-called tangent plane can look like this. Z equals to fxab, fxab times x minus a plus fyab times y minus b. And there is a 0 here because the value is 0. F of ab is 0. So this will be a approximation of this function near the point 310, right? It is a tangent. So now finally we can define differentiability, which try to pay attention on. It looks a little bit scary, but it's actually really intuitive. Just as the definition of limit and continuity, it looks scary as the notation is everywhere, but the point is to understand the concept of the definition. And as for how to sort of manipulate this definition and apply it in various examples, we will see that soon enough, right? So in this case, let me consider some function defined in some domain within the two-dimensional space. Obviously, you can define it for multi-dimensional functions, but let me first focus on the two-dimensional function because every dimension larger or equal to 2 satisfies the same definition. So we say that the function f is differentiable at the point AB, which obviously belongs to the domain, let this following limit is 0. So let us go through this really careful. This is the function itself, right? And we recall from our previous intuition that this is the linear approximation or the tangent plane of the function f at the point AB. So previously we say that we want the first order approximation, right? So simply saying that this guy goes to 0 is not really sufficient because in fact, any kind of function which passes through AB, f of AB actually satisfies this type of limit, right? So simply this guy goes to 0 simply serves as a first order approximation, namely that those two things is intersect at a point AB, f of AB. The two functions share the same value at the point AB. Now, to enhance that kind of concept, we divide things by the distance between x, y, and AB. So we're simply saying that not only that this guy is close to this guy, it is actually close enough so that even if we divide by something that is so small, it is still 0. So let us wrap this up. It's a little bit tricky here. So we see first that this guy is very small, right? Because xy is close to AB. So we're saying that this guy is even smaller so that the quotient is 0. So this is a stronger condition on simply letting this guy to be 0, okay? So not only the numerator goes to 0, also the numerator goes to 0 so fast that it dominates the decay of this distance between x, y, and AB. So let us rewrite this definition and see that it actually matches up with the definition of our previous rephrase of the one-dimensional differentiability. So we see that when n equals to 1, this guy is simply the same thing, f of x, and this is f of a, right? And this would be f prime of a times x minus a divided by x minus a. And if we just put the quotient inside, you will get f of x minus f of a divided by x minus a minus f prime of a. So you see that is basically the definition of differentiability, right? Simply that this kind of limit exists and it actually converges to some number, which is f prime of a, right? So technically, there is a more general way to define differentiability, which is saying that there exists some constant L and M so that this kind of limit holds. And you can actually prove that L and N should be the corresponding partial differentiation on x and y. But simply for not making you confused, I make this definition so that it is more intuitive that we are simply saying that the function itself is only differentiable when a tangent plane serves as a first order approximation. So that sentence is the most crucial one. A function f, a multi-variable function or a single variable function, is the same thing. It's only differentiable at a particular point whenever the so-called tangent plane at the point is actually an approximation of the function near the point, right? That whole sentence is the essence of differentiability. So in fact, there will be some function that have partial derivatives, say fx and fy, but they are not differentiable. So simply having partial derivative does not account for differentiability. Okay, you should be careful with that. There are several examples in the textbook. I didn't cover it here because I figure it is not really important for our scope of course, but I will encourage you to try some exercise in the textbook about the connection between differentiability and the existence of partial derivatives. We will cover all this concept later on by the diagram, but for now, I just want to make sure that you guys are really familiar with differentiability now. Okay, so after that definition, we can well define the so-called tangent plane, which is simply what we get before. So tangent plane, a tangent plane at a point z equals f of xy at a point AB is this guy whenever f is differentiable. So it is only when f is differentiable does this kind of definition make sense, right? Because otherwise the plane, first of all, you might not have some partial derivatives, then you cannot account for this kind of notations, right? Second of all, even if you have this kind of notation, then this plane will not be a good approximation if you're not differentiable. So it only makes sense when we're defining for differentiable function. The tangent plane is actually a plane that is very, very close to the function. Now, linear approximation is exactly the same thing, but we regard the tangent plane as a linear function, xy. So this function is close to f of xy whenever x and y are close to AB. Okay, now let's do some examples with the concept of differentiability. So the first example asks you to show that this function is differentiable at a point 1, 4, and that please find the tangent plane. So for now, the differentiability only follows from definition. That does prove that. There'll be some hard work, but let me go through this step by step. First of all, let's compute the so-called tangent plane, which is constructed by the point itself and the partial derivatives. So first of all, f of 1, 4 is 5. F of 1, 4 at the derivative x is 2, and fy 1, 4 is 1. So we hope that this will be 0. This is the value at 1, 4. This is the partial derivative at 1, 4 respect to x. This is with respect to y. So this is the tangent plane if it is differentiable. It is the plane that we want to approximate the function f. And this will be the distance between x, y, and 1, 4, right? So how do we prove this pink box? First of all, let us simplify notation. So say we set x minus 1, the distance between x and 1, to be h, and y minus 4 to be k. Then we see that, first of all, this is h, so 2h, this is k, so 1k. So this whole thing is simply the tangent plane, right? And f of xy is defined to be x squared plus y. So since x minus 1 is h, so x is just 1 plus h, right? Actually, let me see. I said x minus 1 to be h, yeah. X minus 1 to be h. So you can write x equals to 1 plus h, right? And a similar example works. So when y minus 4 is equal to k, so y is 4 plus k, directly by definition. And now we expand everything and be careful with the algebra. So you see that, first of all, this is simply 1 plus 2h plus h squared, right? That is foiling. So 1 and 4 here combining together eliminates the 5 here. 2h eliminates the 2h, that's good. K eliminates the k, so the only thing in the numerator remaining is h squared. So this pink box accounts us to find whether the limit of this kind of thing actually goes to 0. And we've seen in section 14.2, the limit of continuity, that this should be 0 in the sense that the degree here is 2 and the degree in the denominator is 1. So the decay speed is faster in the numerator. It goes to 0, right? And we can prove that simply by something like maybe squeeze theorem. So obviously this is larger than 0. That's okay. The left-hand side is actually really nice. And obviously it is less or equal to this guy, right? Because we actually increase the, decrease the denominator, making the whole fraction larger. And this is simply the absolute value of h, where as hk goes to 0, obviously goes to 0. You can also prove this by polar coordinate, if you recall that. It is r cosine r squared taking square root. And so, r squared, cosine squared. So if you take the quotient, you'll get r cosine squared theta, which goes to 0 whenever that whatever theta is, as r goes to 0. So we actually get that this is 0, so that this guy holds. So f is differentiable at the point 1, 4. And in some sense, you can derive it even sooner, as soon as you prove that you have the similar arithmetic law of differentiable function. What I'm saying is that addition of differential function is still differentiable, product of differential function is still differentiable, and so on and so forth. Right. So last task here is to find the tangent plane, and we have already find that, right? It is this guy. So you have the tangent plane being 5 plus 2 times x minus 1, and 1 plus y minus 4. Right. So you can see that we cannot do this all day, sort of, right? Because this is already a simple function, x squared plus y. It is sort of a polynomial. If you're dealing with something like sine xy or a bunch of different transcendental functions composing together, then it'll be in general difficult to evaluate a limit. So here we propose a good big theorem, kind of big, differentiability. So we claim that whenever the partial derivative, obviously they have to exist, those partial derivative first order, fx and fy, if they're continuous as a function near the point AB, then we say that f is differentiable at AB. So again, let me get the concept clear. Differentiability means that the tangent plane is a good approximation. That's all. And now I want to find some criteria for differentiability. One of them is this theorem, saying that whenever the first order partial derivatives are continuous, then the function f is differentiable. And in fact, we have some sort of counterexample, which is saying that f might be differentiable at a point, even if those two partial derivatives are not continuous. Okay, so be careful with the logic here. We're always saying if something something, then something something, but it does not necessarily mean that. Okay, let me say this. We're always saying if A, then B, but that does not account of saying if B, then A. It's different. Okay, that is like saying if I get a good grade today, then I will be compliment. But it does not say that if I get compliment, then it must be I getting a good grade, right? It might be I did a great job on teaching, something like that. So, but whatever, the point is to get the logic correctly. So, just to be precise again, we now know that whenever the two first order partial differentiation are continuous, then the function itself will be differentiable. That is a nice criteria, right? Okay. Just so that you guys get how this works, I actually present a proof here, which is not too long. So I am trying to present the proof here. This will not be your quiz. This is not including our scope of course, so you can just skip this part. But I just want to present here for completeness and also to see how continuity of the first order differentiation is important to differentiability. Okay, so if you guys have seen my previous video on the supplement, the limit law, and also the Claire theorem, you can see that whenever I have a continuity assumption, I always first apply that definition and to find a threshold delta so that the corresponding function is close enough. So what I'm saying is that first we fix some epsilon so that whenever x1 and AB are of distance delta, then the partial derivative x has this property. X1, fx xy minus fx ab is always of the distance epsilon, at most epsilon. And the same thing happens for y. That is our assumption of continuity, right? Now we're interested in showing this limit goes to 0. So for convenience, let me define something above here to be d of hk here. So instead of abxy, I used the difference kind of flavor. I didn't use xy and x minus a. I simply replace the x minus a by h and y minus b by k. So I define the dhk to be f of xy, which is a plus h, b plus k, minus the linear approximation. So the goal now is to show that the limit as h goes to 0 or as xy goes to ab, that this is 0. That is a definition for differentiability, right? So now let us see dhk, which is defined as this guy, can actually be written down like this. So let me go through this step by step. This term comes from here, and this term comes from here. And I add an additional term here for the sake of to partial differentiate f here, which we will see later on. And you cannot just add something, right? So let us add another guys here. So to cancel out the previous additional term. And obviously this guy comes from here, and this guy comes from here. And then again, we apply triangular inequality just as what we have said in supplement. So that is basically saying a plus b is always less or equal to a plus b for any number a and b, right? So why is this kind of decomposition useful? You can see that first of all, again, by a really nice mean value theorem stating that whenever some function is differentiable and that the derivative is continuous, then you can always find some c between a and b so that you can approximate the slope by some tangent line, f prime c. So we do that for this term in the x coordinate. That is fx for some alpha, b plus k. So we regard this as a one-variable function, f of x, b plus k. This one-variable function is obviously differentiable and that the derivative is continuous by assumption. So this is what I written down here, where alpha is some number between a and a plus h. And you can do the same thing for the term here, which is fy a beta times k. And since every guy here have a k, I factor out a k. Every guy here have a h, I factor out a h, right? So you see the useful of continuity comes in. This guy, since alpha is between a and a plus h, b plus k and b are obviously within distance k. So since h squared plus k squared is less than delta, these two guys are by construction, okay, less than epsilon. So, actually, I write epsilon. I should use half epsilon just for convenience. So let me change that. There's no big deal because continuity ensures us that epsilon can be chosen arbitrarily. Right. So this will be that epsilon, and the same thing happens for here. You have that epsilon, whereas h obviously is less or equal to h squared plus k squared, right? And the same thing happens here. So we see that. Oh, and yeah, I obviously I put it here where we're just stating that these points are close enough so that this happens. So combining these two terms, we have that dhk divided by h squared plus k squared taking square root is less or equal to epsilon times the corresponding thing, and there's a denominator here. So you get simply epsilon at the final stage. So what are we actually saying? We're saying that whenever x1 and ab are of distance delta, then this guy is less or equal to epsilon, where epsilon is arbitrary. You can choose 0.1, 0.0001, 0.00001. So by definition of the limit, we're just saying that the limit of dhk divided by square root of h squared by plus k squared is 0. And this is differentiability, right? So we see that this is a very good criteria. Again, the proof is not really in itself important. It is just a demonstration of, again, the power of the rigorous definition for limit to show that you have this kind of property, which is saying that continuous partial derivatives ensure that the original function is differentiable, right? Okay, now let us use that theorem to prove some differentiability. Again, in this case, I asked you to show that f of xy, defined by y plus sine of x over y, is differentiable at the point 0,3, and we want to find linear approximation. So let us compute the partial derivatives, which obviously they can be differentiated. You get by regarding y as a constant that this derivative is 1 over y times cosine of x over y. So this guy goes to 0, right? And 1 over y comes from a chain rule where you're differentiating x over y. Same thing happens for y, you get 1 plus x cosine of x over y. And obviously, these are polynomials, and this is a continuous function. So these are obviously continuous whenever y is non-zero, right? So being a continuous function, this partial derivatives are continuous, making f is differentiable at the point 0, 3. And linear approximation is simply the tangent plane we mentioned before. So this is the point. This is a slope along x and y, and x minus 0, y minus 3, which after some algebra you get 1/3 of x plus 3y minus 6, right? So you see that it is better than what we have done before, which is trying to evaluate a limit, and it always take a long time to do that. And things is not always that simple when the dimension is higher. So this kind of differentiability criteria is quite useful. And it actually generalized to general dimensions. You can do it for 3D, 4D, and D. Okay. All right, so those are the examples. And lastly, we introduce a notation on differential. So differential is always a very difficult thing to define. It has a very precise definition in mathematical literature, but it's a little bit difficult to define it in a course like this. So we can simply regard dz here. Say, we're taking a function f of xy. We can simply regard dz, which is the difference between the z coordinate, the difference between the height, to be a very, very, very small difference. So dz, this is a very bad kind of notation. dz is this, which doesn't really make sense, I understand, but it is just a very, 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 very small quantity regarding the change of z. And the differential of dz is defined to be this two guys, fxxy dx, fyxy dy. And you can see why that is kind of intuitive because of the tangent plane approximation. Let us go back a little bit about the tangent plane. Here, you can see that actually we have z minus f of ab. So if I put this here, is fxab, x minus a, fyab, y minus b. So we have actually delta z to be fxab, delta x plus fyab, delta y. This is for the linear approximation, right? It's not the function itself, but it's a linear approximation. So it basically shows that for the function f, you can approximate the difference of z, which is the difference between the different function values, as this combination. So this is the slope along x, and this is the difference of x, and this is the slope along y, this is the difference of y. So in some sense, we're simply using the tangent plane to approximate the difference between 2 points on the plane, right? Let us go to an example. It will make more sense. So in this case, I ask you to use differentials to estimate the amount of matter in a closed cylindrical cake. So closed means that you have a lid, right? And it is of 10 centimeter high. So 10 centimeters high, that is h, and 4 centimeter in diameter. And we like say that the matter in the top and the bottom is 0.1 centimeter. And the thickness of the metal here is 0.05. So we want to estimate the amount of the metal that is used for this cane, which is the very small layer of that metal. So to find out the volume, this is a perhaps elementary or junior problem. You simply evaluate the volume of the larger cane, the exterior of the cane, and you multiply and you evaluate the volume of the interior cane, and you subtract those two things, you will get the metal part, right? And that is quite direct. So first of all, the diameter is 4, so the base is pi times radius squared, which is 4/2, and then you times the height, that is the volume of the exterior cane. For the interior cane, the diameter is now reduced by 0.05 and 0.05, so 0.1, and radius is divided by 2. So this is the base area of the interior cane, interior empty cane, interior hollow. That might be a better word. And this is the new height, right? Because you have to go down by 0.1 and go up by 0.1 inside the cane. So if you actually do the algebra and you do it on a calculator, you get 8.59 centimeter cube. But in general, it is kind of not really necessary to do this because the volume function is actually really nice in the sense that it's differentiable. So we can actually evaluate that using the derivative, the differential, sorry. So let's write down the volume. V is given to be pi times L over 2 bracket squared times h. Here h is the height and L is the diameter. So this is the radius, right? According to our previous definition, the differential dV is equal to partial V partial L dL partial V partial H dH, where we can evaluate this. If you differentiate this by L, you'll get pi times H times 2L divided by 4. So that's L over 2, right? That is the coefficient in front of dl. And then do the same thing for H. It is simply pi L squared divided by 4. So now let us start from the exterior, which is this what did I mention here? This is 10 and this is 4, right? So let us find a difference between this volume and a smaller volume. So that part is dV, right? So if we're starting from the exterior, then you plug in the exterior parameters, which is H is 10, L is 4, and L is 4, and these are the derivatives, right? And now you are shrinking the metal, right? So you get minus 0.1, which is saying that we are shrinking the, we're shrinking the, yeah, here. We're shrinking the diameter by 0.1, and we're shrinking the height by 0.2. So if you evaluate that, you'll get minus 8.8, minus 8.79. That means that the difference between the smaller volume and the larger volume is minus 8.79, right? Approximately. And you can see that that is actually a good approximation in the sense that these two guys are really, really close, right? And this is, in some sense, much easier to compute. You don't have to do any squaring things. Since there's no squareable, actually, it becomes a linear, basically becomes a linear computation, right? The only thing important here is this minus 0.01 and minus 0.2. So I encourage you guys, actually, I insist on you trying this. So we're doing a shrinking kind of algebra, right? To find out this minus 8.79. You can do the same thing by inflating the cane. So in that case, we start from the interior. In that case, this height will become 10 minus 0.2, and the diameter will be 4 minus 0.1. And now this will be positive 0.1. And similarly, this 4, which is the L squared, will be 4 minus 0.1 squared times plus 0.2 because we're increasing the diameter and the height. And you should get a similar answer, which is 8 point, maybe 6 or 7, 9, I'm not sure, but 8 point something. And those numbers are all close to the actual volume, which is 8.5 million. So what I'm trying to say here is that differential serves as it's basically a linear approximation in some sense, and it is very useful whenever you're calculating something really small. So say you have a object that inflates a little bit or shrinks a little bit, then that small difference, dz, can be evaluated by dx and dy, the difference between x and y of the function, multiplied by the corresponding slope, which is fx and fy, the partial derivatives, okay? So simply remember this is the definition of differential, or sometimes we say total differential. All right. Last, we have a very intuitive kind of theorem that is differentiability implies continuity. That also holds in the one dimensional case, right? And so I want to emphasize here that the existence of partial derivatives not only does not guarantee differentiability, it actually also does not guarantee continuity. So what I'm saying is that there might be some continuous function with partial derivative x and y direction exist, but itself is not continuous. So I'm merely saying that existence of partial derivative does not really mean anything. It just means that there is some, it is marginally differentiable, but it does not even guarantee the continuity of the original function. Okay, I will label them in the next diagram so you guys can get a concept. But let's go through the proof here quite fairly because it is very, very simple. We want to show that this guy is this guy, right? That is the definition of continuous. But you can actually do this nice trick. So differentiability tells us that this guy goes to zero, right? Okay, how does this guy come up? So basically what I'm doing is that I add this whole thing here, and obviously you have to compensate that at the last. So what I'm saying is that I subtract this two guy, and I add this two guy. And now I divide this whole thing by the distance between x, y, and ab, and obviously I have to multiply it. Now, why is that useful? Because basically by definition, this guy goes to zero, right? And this guy goes to zero by, again, my definition, x, y goes to ab, right? And obviously these two goes to zero because x goes to a and y goes to b. So everything goes to zero, meaning that fxy actually goes to f of ab whenever xy is close to ab. And that is just some notations, but actually you can go back here to see that, where is it? According to a definition for the differentiability, we see that since the denominator goes to zero, right? So this being this having a limit simply means that the numerator also has to go to zero. And that ensures fxy goes to fab, right? Because these two terms are actually not really important for our discussion. They always go to zero when xy goes to ab. Okay, so that is the implication of continuity on differentiability. Lastly, let us conclude what we have learned for the properties. It is usually referred to regularity property, which is how a function is nice enough. It does not have some corners, which is not differentiable, or it does not have discontinuity. Those are called regularity of a function. So these are some implications of the regularity of a function. Again, I always say that we're working in a two-dimensional space, but every concept here works for 3D space. I guess the only thing that for us now that does not work for general dimension is the polar coordinate. And we will soon see that there is a replacement for that in 3D, which is called a spherical or cylindrical coordinate. But those will be at least covered in chapter 15, I think. Okay, so now let us see. So we have some strong concept, which is the second order partial derivatives are continuous. Then by Claire's theorem, that implies that those two are the same, right? That is in section 14.3, and the proof is in the supplement. So obviously continuity means they exist. That is direct. You have to first exist to discuss continuity, right? And obviously the second partial derivative has to be exist so that the first partial derivative exists, right? Sorry, I'm not saying that right. So I'm trying to say that this has to exist so that that exists, right? So this exists means that this exists. Okay, it's kind of uh tricky, I know. Right. So now the important thing here is that we also include this type of condition in this chapter, in this section, right? Saying that fx and fy are continuous means that f is differentiable. That is a criteria, right? And we know that differentiability essentially means that a tangent plane exists and it's a group approximation. And obviously, fx being continuous means that you have to exist that first order derivative. And we have by our last implication that differentiability implies continuity. So left-hand side here are the strongest condition, and they imply some weaker condition. Okay, that is how this diagram works. So as I mentioned before, there are counterexample for these different directions, meaning that there might be some function that has the second order partial derivative, but the partial derivative is not continuous. This is a rather simple thing to imagine, right? And we know from our, I think, last example in 14.3 that there are some function that these two guys are the same, but this might not be continuous. And the same thing happens here. So obviously there might be some function with fx exists, but fy does not exist. That is quite trivial. And there might be some function with fx exists, but fx is not continuous. That is also quite intuitive. And this is what I mentioned today. So there might be some function that is differentiable, which means that tangent plane is a good approximation. However, the partial derivative is not continuous. That is possible. And lastly, there might be some continuous function that is not differentiable. which is kind of intuitive to based on the fact that we already have some example in 1D space, right? Okay, so again, this is sort of a conceptual chapter, and the only practical part which you can exercise is on the computation of tangent plane. So make sure you know how to find tangent plane for a differentiable function. And to understand that differentiability in high dimensional space is simply saying that tangent plane is a first order approximation of the function itself. It actually goes very nice like this, right? Okay, so that ends our chapter. Um, yeah, and we'll then be covering some practical techniques afterwards, which is the chain rule in multidimensional space. So I will see you guys later.